Good morning. Welcome to day 4 of the Galaxy Formation Workshop. This morning we're starting off with Daisuki Nagai, who will be telling us about cosmology and astrophysics with hot gaseous halos in the era of multi-wavelength surveys. Take it away.
Sorry. Okay, can you hear me better? Okay, thank you. Sorry. We're entering in the sort of golden age of big data science, where the large multi-wavelength survey from optical to microwave, X-ray, are actually providing a large amount of data set that will be mapping out the distribution of galaxies, gas, dark matter through gravitational lensing, and they're giving us the detailed insight into the structure formation of the universe over the next decade. So it's a really exciting time that it's going to be very data-rich, data-driven area at the intersection of cosmology and astrophysics. And this is just an example of the recent advances. For example, from Planck to Rosita, the Planck survey is from microwave, had been detecting all of the galaxy clusters about 10 to the 14 solar masses, and now with the next generation Russian-German mission, Rosita, are pushing the limit of from clusters all the way down to galaxy groups. These are just the data points from EPES, from early data release on 140 square degree survey. Now with the ERAS-1, they're all orders, magnitudes. At the end of ERAS-4, you're expecting hundreds of thousands of galaxy groups detected. It will give us enough statistical power to learn about cosmology and also, hopefully, the gas physics at the same time. One of the major issues with this field is the baryonic effect, the galaxy formation physics, especially in the context of X-ray and microwave survey. The baryonic effects on hot gas profile are one of the most important topics, and we do not have a good enough accuracy in order to exploit the large data set that we're expecting even today. So this is the main topic. In addition to finding galaxy clusters and measuring masses to do cosmology, you can also do map level analysis based on simulation inputs. This is analogous to the cosmic microwave background, where you can do the map level analysis by computing the summary statistics like the power spectrum of CMB, from which that we have learned a great deal about cosmological information. You can do something similar by using the secondary CMB, for example, Sonia-Obzodovich effect imprinted by galaxy clusters and galaxies. Can also create fluctuation. You can do fluctuation analysis and compute power spectrum, which will tell us about both cosmology and also the gas profile in galaxies to clusters. So that's a very exciting area. One of the tension that we are facing, apart from Hubble tension, which you might have heard about, we have another tension in the growth of structure, which is called the S8 tension. A lot of this is driven by the cosmic shear measurement, which is basically giving us a tension on S8 parameter, combination of sigma 8 and omega matter, and that the measurements from CMB seems to be inconsistent with the growth of structure that's based on gravitational lensing. One of the major uncertainty in this area is, again, baryonic effect. Most of the baryons in the form of hot gas in galaxy groups and also in galaxies and clusters, and that is known to have some non-negligible impact at the precision significantly larger than the precision that is required to actually exploit the power of current measurement. Therefore, this baryonic effect is thought to be the basic limiting factor for us moving forward in doing cosmology with these data sets. So this is the sort of the big question that we're facing. So as I said, we're entering in the golden age of cosmology, allowing us to actually exploit small-scale, nonlinear scales. Big challenges are that the baryonic effects feedback, especially on hot gas profile from ICM to CGM, and that we also need a machinery to do multi-wavelengths, create multi-wavelength maps for a range of cosmology and astrophysics to learn and know how. Our hydro simulations are often limited because it's so expensive to a few cosmology, few astrophysics. The full variation is very difficult to do. So my proposal is to actually use computational approaches to actually gain some physical insight into the physics of clusters and galaxy formations. Extract those insights to actually to develop a physically computationally efficient model for astronomical inference or cosmological inference. Really push the frontier from the large scale, from clusters all the way down to galaxies, especially in CGM, and then possibly use machine learning to actually gain more information from these data sets. So just start with some of the work that we've been doing on galaxy cluster size, where we see everything, dark matter, gas, and stars, including metals out to very large radii. So this is sort of a good test bed for galaxy formation. And just a summary of what we have learned from doing simulation, where we include star formation, feedback, and systematically studying them. There's sort of a two areas. One is the inner region. It's affected by the AGN feedback is the dominant effect. So that has been very challenging, very rich physics. But outside of the cluster core is driven primarily by gas accretion. They are also becoming increasingly nonlinear. Non-thermal pressure due to gas motion are particularly important. There are a few other effects. Substructure, filaments that are streaming in to cluster-sized halos are also shaping the observable, which we need to understand. One thing about non-thermal pressure, as you go out into the outskirts of galaxy clusters, in the region where the gases are accreting, the non-thermal pressure due to gas motions and turbulence are increasing, monotonically increasing with radius. And it depends on the dynamical state of the galaxy clusters. So this is something that we need to really model. This is well understood. It doesn't depend on feedback physics in the outskirts of galaxy clusters so much, as long as you go outside of about 15% of R500. So this is something that's well understood. You can write down a simple analytical model, and it actually provides very good description of modern hydro simulation. So we think we understand that process, and we know how to model it. We just have to make sure that we put that into the model. The other interesting feature is that there is edge to the galaxy clusters, known as flashback radius. You can also study the outer accretion region of galaxy clusters, which seems to be offset from the flashback radius. The accretion radius, accretion shock radius seems to be a factor of 2 larger than the flashback radius, which is interesting because it's not predicted by the secondary infall model. So it's an interesting phenomenon that's going on. Nonetheless, this is another thing that we need to keep in mind as we go from 1 to 2 halo term regime, where you go that where recent current surveys are probing these regions from 1 halo to cosmic web regime in the survey. In the outskirts of clusters, we actually expect the electron-proton equilibration time to be longer than the Hubble time. What that means is that we can't really use hydro approximation. You can't just assume the temperature is the same for ions and electrons. In fact, electrons could be significantly cooler. So you might need to do the two-temperature or kinetic simulations, where you take into account the plasma effect in the outer regions of galaxy clusters. So that's another thing that we might need to think about is can we continue to use hydrosim? And do we need to do the fixed simulations in order to take into account the plasma physics? So that's another exciting topic, which at the intersection of cosmology and plasma physics. But with all of those insights, we want to develop a simple physically motivated model that allows us to do astrophysical cosmological inference of these surveys. So that's the motivation for Baryon Pacing project, is that we use simulations to identify important features and then develop a simple model that allows us to predict profile of galaxy clusters or function or groups, and extend that down to CGM. The basic model is a spherical cow approximation, where we assume the polytropic model, like we said we typically do in stellar physics, take into account the fact that the gas turns into stars, so stellar mass-halo mass relation, and we also know that feedback is pretty important, especially when you go to the smaller scale. And then that we also learned that non-thermal pressure due to gas motions are important. So we studied it carefully using hydrosim, and then we put that into sort of simple ansatz, which allows us to then parameterize the important feedback physics using a few parameters. There's not too many parameters for non-thermal pressure. What that allows us to do is you can use the halo model to then compute the map level statistics. Like this is SZ power spectrum. And in the context of this model, you can study the impact of supermassive energy feedback, study the impact of gas motion. It's important when you don't have gas, when you don't include non-thermal pressure, you over-predict SZ power by a factor of 2. When you include the proper non-thermal pressure predicted by hydro simulation, this is what's predicted. This is the template that we need to use to infer cosmology and also the cluster astrophysics. And then in the current latest model seems to be able to do a good job in reproducing the SZ power spectrum for example. Another thing you can do is you can use high-resolution Chandra X-ray observation of the SZ selected clusters, which provides very exquisite measurements. The errors are so tiny, it provides very tight constraints on this kind of model. So we can really reduce the parameter space of this model and then calibrate the model based on observations of the galaxy clusters out to redshift of 1.3. You can also use scaling relation of gas mass halo mass relation down to simple solar masses. So once you do that calibration, we can sort of utilize the best information that we have about hot gaseous halos and groups of clusters and make a prediction for what we expect to see in the for example, X-ray sky. In this case, we're analyzing EFED, Eurosita Final Equatorial Depth Survey, and you can take power spectrum like we typically do. It's the first thing we usually try. And then, so this is a prediction from our halo model, calibrated by Chandra data. This is a measurement from Eurosita, just taking the power spectrum of the EFED survey. Seems to be doing a good job. This is not a fit. This is a prediction from our halo model based on Chandra observation, and then this is what we observe from EFED. So doing a good job. Seems to be somewhat over-predicting here and under-predicting here, so there might be uncertainty of the models or maybe the problem of measurement. The point of all of this is that instead of EFED, 140 square degree, with ERAS-4, which will basically do an all-sky survey, significantly deeper. The projected constraints on omega matter sigma is 4 to 5%. So it's an exciting way of actually doing cosmology using X-ray survey. Here, that data is already out, ERAS-1, and so this is the latest constraint on the S8 parameter, which we are measuring and using this kind of model to do that inference on S8 parameter, which seems to be consistent. Another thing we can do is instead of X-ray, we can use baryon pasting to emulate the SZ Sunyap-Zeldovich effect that can be mapped out using cosmic micro background. And this is the halo-based pasting, assuming spherical symmetry. And we can paste that onto n-body simulation. And we can create what the SZ sky looks like due to hot gaseous halo around clusters and PGM. So this is the halo-based pasting. We can do something a little bit more sophisticated using particle-based pasting. Instead of using halo catalog, we can use the dark matter particles and do the pasting of the gas onto the halo of gas as well as also a cosmic web. When you do that, you can capture the sort of triaxiality. You can also see a little bit of cosmic web, not so much in CSV, but significantly in KSZ. KSZ is the effect due to the peculiar velocity of galaxies, particularly sensitive to IgM. So cosmic web contribution is important. You do the halo-based modeling of KSZ effects, this is what you see. When you do the proper modeling, including IgM, KSZ gets significant contribution from IgM, so we should not really be using the simple halo model approach. Particle-based spacing, of course, takes a lot more time, 70 minutes per map for 5.5 degree. Halo-based spacing is a lot faster. So depending on the science application, you can do some quick approaches to do the inference. But for KSZ science, we really need to do particle-based spacing to take into account the contributions. We can use this technique to do create all-sky map. So this is the case where we apply this baryon pasting model to create the all-sky map. It takes about 3 hours per map. On the Takahashi et al. Simulation, there are 108 realization of the light cone map from the for lensing map, and then on top of it, we can paint the halo to create Z map and also the KSZ map using halo-based. So once we have this kind of technology, we can also apply this baryon pasting to create multi-wavelength map, X-ray and, for example, SZ map for any galaxy survey. This is the example of the work that we're doing with Ruby and LHC collaboration. which has the dark matter surface density map on an logic simulation. They're painting galaxies on top of it. We can paint gas on top of it to create X-ray and corresponding SB map. So this opens up this multi-wavelengths cosmology science. And if you use this technology, we can, for example, compute the auto and cross spectra of this is a Compton Y, X-ray, 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 cross correlation with X-ray with Compton Y, and the X-ray with convergence map from gravitational lensing. You can really pull in all of these multi-wavelength data sets. Because our models are pretty simple, you can then vary our models as a function of turbulent non-thermal pressure, stellar mass-halo mass relation, energy feedback, substructure, which is affecting X-ray, and you can study the sensitivity of these astrophysical, sort of key astrophysical processes and how that impacts the map level noise. So this is the kind of a pipeline that we are developing. Once you have them, you can do the simple forecast to apply to real data, hopefully in the future. This is the forecast for what we expect to get when you combine Eros-theta, TMBS4, and Ruby measurements in order to then constrain the cosmology and astrophysics all at the same time. And you get exquisite constraint from X-ray. When you add X-ray on top of it, you can really constrain the non-thermal pressure due to turbulent motion, as well as also clumping, which is boosting the X-ray signal. So you get a lot of constraints from X-ray, and that you can reduce systematic uncertainty due to that. That leads to the improved measurements on cosmology and motion feedback. This is the kind of the exercise that we like to do over the next decade, and we're developing a pipeline on that. Maybe I will skip this, just that we also have a way of measuring scatter in addition to mean profile as a function of halo mass. So ask me if you have any. I would like to switch the gear, that we're kind of new frontier, is to go from galaxy clusters, where we can map out both the thermodynamic quantity as well as metals, all the way out to virial radius, or the entire virialized region. Now, I think the exciting topic is to actually do something similar for hot gaseous medium around galaxies. So that's called the circumgalactic medium, which this field was pioneered by quasi absorption line with Hubble Space Telescope, which gave us a hint of what might be going on. There was like a warm hot gas out there. But in the future, we are expecting significant observational advances on this topic. First, the sensitivity in TMB and X-rays are pushing the detection limit all the way down to about Milky Way size objects. In X-ray, in low redshift universe, SB effect is insensitive to redshift, so then you can really probe. If you do the stacking, for example, you can then probe the Milky Way size objects out to arbitrary direction. This will give us not just an absorption, but an emission. We can map out the entire thermodynamic quantities around galaxies out or wherever the galaxies might exist. Another exciting topic in the past radio bursts with time and many up-and-coming observations is really actually also pioneering our ability to actually study CGN, especially below redshift 1, where we expect to see sensitivities in addition to absorption. So so that's an exciting future over the next decade or so from surveys, which is complemented with a more targeted observation of galaxies. On the theoretical front, there's a new set of simulation called CAML. You can now do simulation of different kinds of subgrid physics, and you simulate the same box many hundreds and thousands of times, and to actually do parameter studies as a function of cosmology and astrophysics. So this is a project that we're doing with CAML's collaboration, and we can basically create X-ray maps with galaxy positions as a function of cosmology, like sigma 8, as a function of supernova feedback, as a function of AGN, because you have thousands of simulations where you vary these quantities one at a time, and there are many realizations. We can study how observable changes as a function of those key physical properties. I'll just talk about a few takeaways from the CAML simulations. For example, we've learned a great deal about how baryonic physics affect the matter power spectrum. And in fact, there's a particular quantity called the baryon spread. How much baryon is spread due to feedback. You can quantify that within simulation, how much baryon is kicked out relative to original dark matter position. You can measure that in simulation. And it turns out that the amount of baryonic effect that, on the matter power spectrum depends very sensitive on this theoretical quantity called baryon spread. The only problem is that that's not really observable. So I will give a shout out to the talk by Isa, who actually found observable way of measuring the baryon spread, but using FRBs. So I'll stay tuned for her talk that there is sort of exciting universal relation between the observable and theoretical quantity, and this is for the range of simulation. SIMBA, PNG, Astrid model for a wide range of cosmology and astrophysics, they all lie in the same curve. What that means is that if you use the FRB to measure this thing called F parameter, which I will tell you more about, you can measure baryon spread regardless. We can do something similar for X-ray and SZ. Now we have this fairly rich model that we can use to train. We've developed this thing called emulator for functional cosmology and astrophysics. So you can create X-ray map, SZ map, just for a wide range of cosmology based on this as a base data set. I will skip this. You can also, or maybe just briefly mention that you can also use machine learning using sort of simulation as an input, and instead of using just X-ray, if you add, for example, H1 measurement, whole gas, that actually adds more information about our inference on CGM mass, halo mass. You can start to actually use simulation-based inference on measuring CGM properties from various surveys. So we're exploring how we might be able to actually do that. And last but not least, instead of machine learning approach, there's also a need for getting a physical understanding of how CGM profiles are affected by various models. There are a couple of physically motivated models. I talked about baryon pacing model, but there are other models, isentropic, cooling flow, precipitation models. So there's sort of important research that needs to be done to compare various physical models of hot gas in CGM. So there's a recent paper that we put out where we do the systematic comparison of hot CGM gas flow. So maybe I'll stop here. I just want to leave you with this summary that we're, I think, really entering into the exciting time for cosmology and also astrophysics, and we can use galaxies and clusters and cosmic web as a way of actually learning about advancing the field forward. Thank you.
Thank you very much, Daisuke. Very exciting things coming up. Any questions?
Hi, a very nice work. I had so this the baryon shift that you're showing up there. Do we know the relative contribution between supernova feedback versus AGN feedback that's causing that shift?
So that's a great question, and it depends on which simulation. This is actually for the SIMBA simulation.
Right.
So it really depends on which simulation that you're looking at, and also how they're implemented.
Right.
In most of the contribution in the relevant range are in galaxy groups, and there the contribution of AGN and supernova are almost equally important. If you go to CGM, the supernova becomes more dominant.
Okay.
We will take maybe one more question.
Yeah, thanks for the talk. Very nice work. So regarding your last point, it depends on simulations. So this is critical for SBI. So how are you dealing with all these simulation-dependent biases when you do SBI?
So I think that this is sort of the key takeaway. That we are looking for example, you can use things that there's no way that we can. It's very difficult to understand. Like subgrid physics is, as many of us know, that it varies significantly. It depends on what you learn. But we can ask the question, for example, can we find observable that tells us something about important quantity in simulation in a way that doesn't depend on galaxy formation physics? That's the kinds of questions that would be particularly useful. And here, this is one example where we think we found that kind of universal relation that doesn't depend on the subgrid physics or dependent physics. It does not really depend sensitively on cosmological nor feedback. So here, we're trying to make a relationship between F parameter in FRB and baryon spread, and then that we found this is what we call sort of seemingly a universal relation, because it doesn't depend on which simulation, that particular curve doesn't depend on whether you use SIMBA, ASTRID, TNG, and then we have a significantly strong AGN or very weak supernova. All of those models are in there, yet we find this relation. So this kind of simulation could be useful for finding observatories that will tell us some physical quantity without really knowing details of subgroups. I think there are very small set of questions that can be addressed, and we're looking for that kind of relation. So I think this is the path forward.
Thank you so much, Daisuke. Let's thank him again.